It's a great pleasure to be here. So when I arrived here like 20 years ago, a bit more, as a young postdoc, I came in, everybody was very friendly. I got a beautiful office here. There was coffee in the morning, there was tea in the afternoon. And I thought, okay, life as an astrophysicist isn't so bad after all. So here we go. 14 orders of magnitude. So what I will be mostly talking about is the question of whether black holes, massive black holes, can form in dense star clusters. And this is a complex problem, as you will see. We see dense clusters. This is R136 in the LMC. It's one of the densest clusters nearby. 10 to the 5 solar masses are so very high densities, 10 to the 4, 10 to the 5 solar masses per square parsec in the center. But now recently, we also see clusters at redshift 10, which are probably, this is a reconstructed source plane image from Adamo et al., about the same mass. Each of these blobs is about the same mass, same size, same dimension. So it's interesting. And this will remain a fundamental science question, I think, in the area of upcoming observational facilities, JWST, ELT, LISA, and so on. But it's a great challenge for computational astrophysics. So I have to put this plot here. Martin Rees has basically formulated all the science questions quite a while ago. And I like George's quote, this plot has terrorized theorists since then, which is actually probably true. So why is it such a difficult problem? So you start from a gas cloud, which comes from, as a collapse of the interstellar medium, multiphase interstellar medium in a galaxy. The cloud collapses, forms stars on 10 to 100 parsec scale. Stars interact with each other. You can form a compact star cluster, and all the way down to stellar interactions, stellar mergers, tidal disruption of stars, and eventually the merger of black holes. So this is 14 orders of magnitude or more. Now, this plot is very complicated, but a colleague of mine pointed out a relatively funny part, well, if you think about it, funny part of this plot. All these complicated physics. But then here, there's this spot which says, oh, if none of this works, one black hole spectacularly grows by accretion. I like this, almost an instruction for galaxy formation subgrid models. Okay, so seriously, what is the basic idea? Why could we form massive black holes in dense star clusters? So this goes back to early n-body experiments. You have a dense cluster, low metallicity helps because then the stars don't lose mass so rapidly. Massive stars quickly sink to the center. They can merge, they can build up higher mass stars and either grow supermassive and collapse into black holes, or you can have stellar collisions, black hole mergers, collisions between stars and black holes. So there are a number of experiments, there are many more. I just highlighted a few. And this is an early paper by Simon Portuguese-Swart showing the build-up of supermassive stars in a dense star cluster by stellar collisions. And then these massive stars collapse into probably intermediate mass black holes. On the right, this is a result of an experiment which basically is a traditional experiment. You take a globular cluster-like system, evolve it, and look for black hole mergers, and these are mass ratio plots, for two different experiments, and we can actually reproduce the typical mass ratios of black hole mergers observed by LIGO and gravitational wave detectors. So this is the n-body part of the problem. It's difficult enough. Now, then there's a little side note I want to make because I'm here at IOA, and the n-body, is really Sverre Arset to some degree. Sverre Arset's work, okay? It started in 1963 or so, and then he built codes from n-body 1 to n-body 7, really accurate and fast codes. And the two examples I showed you are two different incarnations of Sir Arset's codes. And there's another piece of work that was done here, Jared Hurley and Chris Tout, is the making available fast stellar evolution tracks, okay? Highly influential papers, SSE, BSE, many people, you have used them. We have used, or still use them, but they're updated, but it's very, very influential. By the way, Sverre seemed to be one of the first one who did structure formation simulation, cosmological structure simulation formation simulations. This is paper 1. I think there was never a paper 2. I don't know why. Maybe other people took over. And this, I found this, which I found interesting. It's an assessment of the present state of the gravitational n-body problem. And there's a sentence here which computational people can use still in their applications. The development in recent years, digital computers, high-speed storage, entirely new possibilities. Okay, you have to just replace by several hundreds by 10 to the 9 or 10 to the 10 bodies now, but the sentence is exactly the same. 1964, early days of computational astrophysics. So there's another aspect of this, and this is the hydro part. So what happens if the gas cloud collapses? How do you form stars? And there are many, many studies looking at how do you form stars in fragmenting clouds, how do they interact, how do they stop star formation, how do stellar winds, protostellar outflows, radiation, supernova explosions influence the star formation efficiency and so on. There's vast literature, and I just start here from very influential early work, Matthew Bate and Ian Bonnell, all the way down to recent work, Rudich et al. I've sorted by color table. And this is a tough problem. It's a very important and very interesting problem, but I will not talk more about this other than show you recent developments. So these simulations were limited mostly to small clouds, 100 solar masses, 1,000, 10 to the 4 solar masses. But recently, because of there's more interest in massive cluster formation, there have been attempts also in the previous plot, but I highlight those, attempts to do the hydrodynamical collapse simulation and couple them with more accurate integration scheme for stellar orbits, for stellar motion. And there's an example here using a fourth order Hermat integration scheme. There are coupled approaches, a Muse framework, Torge Muse framework. This is work with the PETA code, which is a fast n-body code developed by Long Wang. And this is a recent paper, a science paper by Fuji et al. Using SPH code coupled with also the PETA code. And they find that if you do the hydro collapse and the stellar evolution and account for stellar mergers, you can actually form supermassive stars or very massive stars, and which eventually collapse into black holes or massive black holes. Details. They're important details which we have to take into account. But most of this, what I showed you, is idealized initial conditions, spherical clouds, turbulent clouds collapsing. And there's an interesting paper here by Holly Katz and Deborah and Martin Henold here in 2015, which I liked a lot. It was a bit ahead of the time, I guess, with using cosmological zoom, very high redshift cosmological zoom simulations, and then further evolving the clouds with n-body code to see whether they can collisionally form massive black holes. Now, and here's the galaxy connection, okay? Because these clouds and these clusters have to form somewhere. So how can we model this? And what is the prerequisite to actually reliably model this? So what we require to do this in a galactic context is actually to resolve the multiple phases in the interstellar medium. Now here's the star at the word resolve. If you read the word resolve in a paper, don't believe it. It's never resolved. It just capture. These models should capture basic properties. You know, the composition, this is temperature density of the hot, warm, ionized, neutral, and cold phase of the ISM. And the models should capture the basic cycle of the gas, okay? So you have hydrogen gas collapsing to star-forming densities. You have feedback, H2 formation, supernova. You move the gas here, and then you cool and collapse down again, okay? This requires orders of magnitude temperature and density. It also requires including physical processes which can follow this. So here's an example of such a simulation. And I here talk about only simulations which realize in one way or the other individual stars in the simulations, but I will tell you later why I think this is, why I focused on this, okay? This is an example, you know, the Griffin project, which we have started working on since 2016, and most of the very interesting recent work is by Natalia Lahen, who is a fellow at MPA. So this is what we can do in the phase diagram. So we can pretty well cover this space. We have star formation here, and this is just the pressure version of the plot. You know, we have a three-phase medium, hot, warm, and cold. And we have models for cooling, low metallicity, low temperature cooling, stellar winds, H2 formation, H2 region formation, and so on. This is one, just as a nice movie, this is one of the biggest simulations Natalia has run. This is a dwarf galaxy disk. You see new stars, gas, temperature, pressure. You see all this very beautiful structure, outflows, and so on. You see little star clusters forming. And I will talk about this a bit more in detail later. So this has become an extremely active field in the last years. Just highlight a few other groups who have been working on this. And I think this problem has now been tackled with almost every numerical method you can imagine: grid codes, moving mesh codes, SPH, MFM. So this is results by Emmerich et al. For a dwarf galaxy, also star-by-star simulations. And the point they were making is that it is very important to treat photoionization accurately, because you might miss some of the simple approaches. Just take a Strömgren, like we are doing, just a Strömgren approximation. So you heat gas around newly forming stars. And they say this is very important to get the structure right. This is ENSO simulations. This is a set of Arepo simulations from Smith et al. Also very nice, also highlighting the importance of ionizing radiation for the formation, for the truncation of formation of clusters. So it seems that the massive clusters are very important for driving the feedback. And if you include ionizing radiation, you truncate the massive cluster formation and you reduce the outflows. So basically also highlighting that in this game, it is very important to include basic implementations for all these physical processes, because you get probably cluster mass functions not correct. This is another example of the Asura collaboration. Also, the Fuji paper I showed before is part of this. They also did cosmological simulations, and they also have a nice IMF sampling for star formation down to very low masses, which is important, and I'll show you later. Ramses simulations of the same type, Anderson et al. They have been looking at, for example, runaway stars, the effect of runaway stars on the ISM, on the outflows, and so on. And MFM, measures finite mass, particle-based hydro, Steinwandel et al. So these are just a few examples. So this is a very, very active field, and it's about time to do something else. Okay, anyway. Now there's a problem which we have. So we have the structure of the interstellar medium, and we form star clusters, but whatever we did, none of the clusters looked good, okay? They have reasonable mass distributions, polar mass distributions, but if you look at the scaling relations, Hislop et al., scaling size, surface density with mass, they're all off from the observed relations. So what we have changed star formation efficiencies, we have changed feedback, we have turned on and off photoionization, and so on. We have the cloud properties right. So we were really surprised. We thought that we got the feedback wrong, which is probably fine because we can't resolve it. Now, it turns out that was probably not the reason, okay? And I tell you why. So we had these clusters, and the best models we had, the clusters were very compact, and they stayed compact for all their lifetime, and they never dissolved. So then we realized that maybe we are missing stellar dynamics here already. And of course, it's plausible. We just didn't think about it. And so Natalia Lahen did something very, very nice. So she used a method that we had originally developed for supermassive black holes. Okay? So in large-scale simulations, you have your supermassive black hole, but you have to compute the interaction with the stars correctly. We put a little regularized region around it with an algorithmic regularization method, which also started here actually in Cambridge, Carl et al., and also Martin and Sverre were involved, but actually the pioneer then in the end was Antti Rantala, who is also a fellow at MPA. So you put this regularized region around the supermassive black hole, and then you can accurately integrate the orbit. Okay, higher order integration scheme, very, very accurately, and it's very efficient. So Natalia used this technique and now puts a regularized region around every massive star we form in the simulation. Okay, we sample in the simulation. And this is important because the massive stars drive mass segregation, and the massive stars are also the ones who sink to the center and would like to merge. Okay? And when we do this, we get actually a dramatically different size evolution of the clusters. So they form compact, but then they segregate, and then they are stripped in the tidal field of the galaxy, which is what we all would expect to happen. We just did never see it in simulations. So here, and just to make sure that this is good and new, I wrote down this is good and new. These are clusters in Natalia's simulations. They form very compact, but quite rapidly after a few million years, they increase in size and move on to the observed mass-size relation. In our traditional approach, which was high resolution, but the lower order integration scheme and softened gravity and so on, they just stayed compact and were hanging around. And Natalia made a very nice comparison movie about this. And so this is the old and this is the new version. And I only show the new stars here. And at first you don't see much of a difference, but then at some point you realize these clusters actually disrupt in tidal streams and join the smooth stellar distribution of the galaxy. Okay, this is great. It might look a bit, not spectacular here, but this is great because it seems for the first time we have a simulation which can form and dissolve the clusters kind of self-consistently. And this is shown here. If you look at the number of cluster stars and the size, with the newly implemented integration scheme, you see dramatic mass loss as we expect, and you see a very rapid size increase, which is very plausible also from theoretical considerations. This is on low mass clusters, but I wanted to talk about high mass clusters. So how do we make high mass clusters in a realistic galactic environment? You can do cosmological simulations, very expensive and difficult to control. We did something very simple. We just took two low mass, very well-resolved galaxies, smashed them together, and to create a starburst. So an extreme star formation environment, okay, very extreme environment. And this is an example of the simulation. You see the newly forming stars here. This is gas, surface density, and temperature. So we have all these cold blobs, which are cold clouds here, which form. And then we have these stars. So every point here is an individual star. We have these clusters. We have the rich population of star clusters. So Natalia looked at this, and also another student, Konstantina Fotopoulou, she looked at the cold cloud properties of the simulation. And this is the mass function, which looks reasonable. It's minus 1.8 is the observed one is here. And this is a time sequence early on, and then you have the merger, and then it goes down again in normalization. It's a polar mass function, so It's what you expect from a fragmenting cold interstellar. And out of these cold clouds form the star clusters, which also follow power mass functions, which are observed, okay, all the way up to, the most massive one is 10 to the 6, or almost 10 to the 6, and this is a comparison with LMC, SMC star cluster mass functions. So our interpretation is the massive clusters here are just in continuation of the normal star formation process in very, very extreme environments. Now, if you look at the formation of the three most massive clusters in this simulation, they all have 10 to the 5 solar masses. So you see the first one forming here, a very short timescales here. This is like 20 megayears. First one forms here, and then the second one forms, and then the first one moves down here and creates a super bubble, okay, which drives gas into this region. And I will show a zoom in into this region, and this is how this most massive cluster forms in this simulation. And this movie takes 10 mega years, okay? It's very short. 10, 12 mega years, 20 parsec scale. Nothing is here, and then we start it. This is stars, this is gas surface density, temperature, pressure, and you see protoclusters forming here. Look at the time, it's not a galaxy formation simulation, so this is little protostar clusters. They form, they come, it's a converging flow. It's a very extremely highly dynamical, rapid mass inflow of gas. Then the super bubble hits here, compresses the gas. You form two more massive clusters, and then they accumulate into the very massive cluster. And if you analyze the cluster mass function at any time in this picture, it's a power law, okay? It's quite remarkable. And so we looked at how can this cluster assemble and why, and what are its properties. We have gas surface density at different times here, early, late, but the gas surface density dashed line here never exceeds this never becomes very high. However, the stellar mass, the solid line piles up, okay? So you drive in gas, you form stars, you pile them up to densities of 10 to the 5, 10 to the 6. So extreme dense environments which we can create relatively normally in our simulations and not unlike what is observed in very, very, very dense and massive clusters. Now, we have used this as a motivation to rework or to rethink about the massive cluster assembly. And Antti Rantala has done amazing work. So he basically wrote a novel fourth order forward integration scheme for n-body problems. It's highly optimized for GPUs. We thought about a fourth order forward integration scheme, which, because it can later be easily coupled with hydro, it's a bit more difficult because predictor-corrector schemes don't work with hydro so well, like Hermite. So very efficient, coupled to stellar evolution, including post-Newtonian corrections up to 3.5 order. So he set up a region with a power law cluster mass function, 10 to the 6 solar masses roughly, realized with individual stars, including stellar evolution, merger prescriptions, and the black hole mergers are done self-consistently because they are post-Newtonian corrections. And so he submitted this paper, and then Angela's paper came out afterwards. And it seems, if you look at the brightest clusters here, which are 10 to the 5 solar masses, he basically accidentally, probably simulated the evolution of this system. So what happens in these subclusters, massive stars form, very massive stars form, and they collapse, and they can collapse, and they form, might form massive or intermediate mass black holes. And he provided these wonderful merger trees, okay? So you start with a massive star. The massive star likes other massive stars. They merge. There's always one massive star which taking over the process in the subclusters, and then it collapses into a black hole. In other subclusters, the same thing happens as well. And then you have black hole interactions. And these black hole interactions can result in triple interactions, very complicated triple free body ejection, all of the processes which are in Martin's 1978 plot. slingshot ejections, and some of them actually merge by gravitational wave emission. They get recoil kicks, which we also follow, and then they are ejected from the system. But other systems, like this one here, retain their most massive black hole, and it grows up to a few thousand solar masses on timescales of like 10 mega years. Okay, this has to happen fast, because once the massive stellar evolution is over, very little happens in these clusters. And what is the prediction for gravitational wave sources? In this case, we go up to 1,000 to whatever 100. So like this scenario would actually predict intermediate mass black hole mergers, okay, which we cannot detect at the moment. So what is the frontier? Here, I think cosmological simulations, I think of early nuclear cluster formation would be very, very interesting, but extremely complicated if you do it at high resolution, star by star basis, and you would have to include the relevant integration techniques. This is something we have to think about. So what's up? I think the massive black hole formation in massive star clusters is a very interesting process because it's natural. If massive cluster formation is normal star formation, there's nothing special about it apart from the environment. Okay, just extremely dense and low metallicities. What are the prospects for nuclear star clusters? You have these star formation events. I was talking about single stellar populations evolving, but nuclear star clusters will have repeated episodes of this. So every episode will start a new cycle of this process and might actually boost the formation of massive black holes and their accretion. It's an interesting theoretical problem because it closes the gap between stellar evolution, hemodynamics, hydro simulations, and galaxy evolution. That's great. Those used to be different fields, completely separate fields 10 years ago. And it also connects to the current and future observational facilities. However, there are still significant uncertainties. We still use subgrid models. Every highly resolved model still uses subgrid models. We have to be careful. We have to write and maintain the very, very huge codes, simulation codes we have to use here. There are uncertainties in the binary evolution, single binary evolution, stellar evolution models. We have to worry about the cosmological context and also worry about other observable predictions. One was the gravitational wave, which cannot be detected. And I think we will know more. I wrote this down before you, Carlos. We will know more at IRA 100. Thank you.